My friends, today is a sad day. We have lost a dear and close friend, and all of us are mourning. It's Sigma, and it's time for Sigma to be gone. But despite how hard this is for us, I'm here with you, and we'll get through this together. But let's be honest, how realistic was Sigma? Imagine that you're testing the mu, you don't know the average, but somehow you magically know the standard deviation. So we've had Sigma for a long time simply because it's easier. Let's talk about a more realistic scenario. What happens if you don't know Sigma? So true story, once upon a time this wasn't an issue. Everybody just assumed they knew Sigma. How were they getting magic Sigmas? They would look at the data and they would calculate the standard deviation, which is what we did in chapter 1, and then they would put that in as if it was Sigma. So for this case, our average, I put a little 5 to remind us there's 5 data points, is 5.196 with a sigma of 2.52. Now, we call this x bar not mu to remind ourselves this is not the true value. We hope it's close to mu. Well, this also is not the true sigma. It really should be S. And true story, William Gossett, he worked for the Guinness Brewery Company in Dublin, Ireland, and his job was to bicycle to work, and then he would taste test the beer. He was also studying crop yield and all sorts of things about the barley and what they were using, and then he would bicycle home. So 5 drinks was a lot for this guy on his bicycle ride home. And he was using X bars and sigmas, which were really S's, and what he found is they didn't quite fit the normal distribution. His data was looking more like this. The normal distribution has a very specific curve shape, and he was getting curve shapes that were flattened out. Why? Why was this happening? He discovered there was a little bit of extra error right there. Where is that extra error coming from? It's coming from S is not quite sigma. And it's actually kind of difficult to estimate sigma well. You need a lot of data to get a good estimate. So because he was not getting a perfect sigma estimate, his distribution was a little fatter. And he discovered this new distribution and went to his bosses and said, hey, we can improve our statistics by using this new distribution. I've called it the T distribution instead of the Z distribution. And the people at Guinness said, we don't want you to publish because we want you to work for us and we don't want other companies to have this. And he said, look, other beer companies aren't going to realize how they could be using statistics. If I publish this, it'll take them 100 years to catch up. And they said, well, we'll let you publish on 2 conditions. 1, you don't mention who you work for or how you're using it. And 2, you have to publish under a fake name. You can choose the fake name pupil or student. And so this is called student's T distribution because he published. And now, 100 years later, we know the whole story. It's not 100 years later. Do I have? Let's see. He's on Wikipedia. 1906. It is 100 years later. Okay. So now the hard part about this is this error is based on S and sigma being different, and that changes based on the sample size. With a sample size of 5, there's a lot of error here. But what would happen if we changed our sample size to 50? Well, we would have a lot less error. And this would look a lot more like the normal distribution. What if we had a sample size of 5,000? Well, the Z and the T are going to be awful close together. So what Mr. Gossett did is he created this table of how you could look up t-scores to get p-values. And on his table, he had 30 rows, and then his paper ran out because back then printing presses had 32 lines and he had a title. And so at the very end, he said, just assume that it's normal. And that began the whole idea that once you reach 30, we get normality. So now you know where our magic number 30 originated from. What I'm trying to emphasize is the idea that if you want to do the T distribution, how large your data is matters. And so that's based on what we call degrees of freedom. And for right now, the degrees of freedom are very simple. It's n minus 1. Later we'll talk about other scenarios where your degrees of freedom might be different. What degrees of freedom says is if I knew the total, how many of my data points would be made up? In other words, if I told you the average was 5.196, but I didn't tell you these numbers, could you be able to tell me what these numbers were? Well, no. But what if I told you this number, this number, this number, this number, and I told you it averaged 5.196? Could you calculate this guy? The answer is yeah, it would take a little bit of work, a little bit of math, but you could figure out what he is. So given the average, these n minus 1 data points are random, but that last data point is not. So degrees of freedom is n minus 1. You've seen this before. Where? Look at the equation for s. And in the denominator is the n minus 1. So there's some mathematical reasons that we're not going to get into right now why this degrees of freedom is n minus 1. What does it mean for you when you're finding a p-value? Look at the applet. So far, everything that we've done in this class is always using z. Now, if you don't know sigma, if you're getting an s from the data, we're going to switch to t. And I'll show you some examples of how to tell whether it's t or sigma, because we are still going to have old z-tests in there. Notice when you switch to t, you get degrees of freedom popping up right here. For us, the degrees of freedom are 4 because we had 5 data points. So now when I put in z-scores of infinity, really? What? Oh, that's a p-score. Do not put in t-scores in the p-value box. It will make you look very foolish on a video. But if we put in our t-score, and my camera window I don't think is enough to capture, can I scoot it? Yay, okay. Point is, now we get our p-value 0.0506, and it'll draw just the same. So t-scores and z-scores are going to work the same for our applet as long as you can watch that degrees of freedom.